You are falling right now. Even sitting still in your chair, you are being pulled through curved space at this very moment. The truth about gravity is stranger than anything you are taught in school. It is not a force, it does not pull, and it bends time itself. We will travel through space that ripples like water, through clocks that run slower near the ground, past black holes that twist reality into knots. If your mind enjoys being broken open, hit like and subscribe so we can keep going deeper. Forget everything you think you know. We begin. You have seen the picture 100 times. A stretched rubber sheet, a heavy bowling ball sitting in the middle, a smaller marble rolling around the dent it makes. Teachers love this image. Textbooks love this image. Documentaries replay it on loop, and almost every part of it is wrong. The trampoline analogy is meant to show how gravity works. A massive object sinks into space, and smaller objects roll toward it. Simple, visual, satisfying. The problem is that this picture only works because of the very thing it is trying to explain. The marble rolls toward the bowling ball because Earth's gravity is already pulling it down onto the sheet. Remove gravity, and the marble does nothing. The whole demonstration cheats. That is not the only flaw. The rubber sheet is flat and two-dimensional. Real space is not flat, and it is not two-dimensional. We live inside 3 dimensions of space, woven together with 1 dimension of time. 4 dimensions, all twisted into a single fabric called space-time. No rubber sheet can show that. No bowling ball can dent it the way the sun dents the cosmos. Here is what the analogy almost gets right. Massive objects do change the shape of the space and time around them. The sun warps the geometry of its neighborhood. So does Earth. So does your body, in a way too small to ever measure. But the warping is not happening in some flat surface beneath us. The warping is happening in the very stage that you live on. The room you are sitting in is bent. The air around you is bent. The path of every photon entering your eye is bent. When a planet orbits the sun, it is not being tugged by an invisible rope. It is gliding through a region where space and time have been stretched. It is following the easiest, straightest path available in that curved geometry, the same way a marble rolling across a warped floor curves without anything pushing it sideways. The marble feels no force. Neither does the planet. This idea sounds harmless until you sit with it. Then it starts to crack the way you see reality. Because if gravity is not pulling on things, then what exactly is happening when you drop a coffee cup? What is happening when you stand on the ground? Why does your weight press into the chair beneath you right now? The Newtonian answer feels obvious. The Einsteinian answer feels wrong at first, and then it feels impossible, and then it feels true. Scientists have tested this picture for over a century. Every test has agreed with Einstein. Gravity is geometry, mass and energy curve space-time, and curved space-time tells matter how to move. That single sentence overturned 200 years of Newton and rewrote the rules of the universe. The trampoline image will not die because the truth is harder to draw. You cannot sketch a 4-dimensional warp on a napkin. You cannot animate it without lying a little. So the bowling ball stays, the marble stays, and students grow up believing gravity is something that grabs them from below. It does not grab, it does not pull, and what it actually does to you, every second of your life, is something far stranger. Stand up, sit down, walk across the room. You feel heavy, you feel pressed into the ground. Every muscle in your legs is fighting against something that wants to drag you down. That feeling, that constant pressure, is not gravity. Read that again. The feeling you call gravity is not gravity at all. According to Einstein, you are not being pulled toward the floor is being pushed up into you. The ground beneath your feet, the chair beneath your back, the bed beneath your body at night, all of them are accelerating upward against your skin. That upward push is what you feel as weight. The actual phenomenon of gravity, the curving of space and time around Earth, produces no sensation at all. This is one of the strangest ideas in all of physics. And it gets stranger. Imagine the floor suddenly disappeared, the carpet, the concrete, every layer beneath you gone. You would not feel a sudden tug. You would not feel a force grabbing you. You would feel nothing. The pressure on your feet would simply vanish, and you would float for a moment before the rest of your body caught up. Then you would fall, and during that fall, you would be weightless. A skydiver knows this feeling. The moment they leap from the plane and the wind has not yet caught them, there is a stretch of pure silence in the body. No weight, no pull, just air rushing past skin. Their bodies are doing exactly what your body wants to do at this very second, but cannot, because something solid keeps stopping it. You are not being held to the earth. You are being blocked from falling through it. This idea has a name: the equivalence principle. It says that being in freefall is identical to being in deep space with no gravity at all. There is no experiment you could perform inside a sealed falling room to tell the difference. None. Drop a pen and it floats beside you. Pour water from a cup and it forms a wobbling sphere. Your hair stands out from your scalp. If the windows were blacked out, you would have no way to know whether you were plummeting toward concrete or drifting between distant stars. That truth has a brutal consequence. The next time you trip on a curb, the brief moment before you hit the ground is the only time you are not experiencing the strange pressure of resisting your natural path through curved space-time. Your body, for that fraction of a second, is doing what physics intended. It is moving the way an unstoppable, unforced object moves through warped geometry. The collision is what hurts. The fall does not. Astronauts orbiting Earth feel weightless not because they have escaped gravity. Earth's pull on the International Space Station is still about 90%, as strong as it is on the surface. They feel weightless for the same reason a skydiver does. They are falling, constantly. They simply happen to be moving so fast sideways that they keep missing the planet. The whole planet is missing itself in slow motion. The ground is the only thing stopping the universe from quietly demonstrating what gravity really is. And the way it stops you is its own kind of miracle. There is a myth almost everyone learns and almost no one questions. Astronauts float in space because there is no gravity up there. It feels obvious. They are far from Earth, they are weightless. So gravity must be gone. Wrong. Gravity is still grabbing them with nearly the same strength it grabs you. The International Space Station orbits about 250 miles above the planet's surface. At that altitude, Earth's gravitational pull is around 90% of what you feel right now reading this. If you could build a tower that tall and stand on top of it, you would weigh almost exactly what you weigh today. You would not float. You would crash through the floor like a sandbag. So how do astronauts drift like ghosts inside the station? The answer is one of the most beautiful tricks in physics. They are not floating. They are falling. Forever. Around the planet, instead of into it. Picture this. You stand on top of a mountain and throw a baseball as hard as you can. It curves down and lands 100 feet away. Throw it harder. It lands a mile away. Now imagine throwing it so hard that as it falls toward the ground curves away beneath it. The Earth is round. Its surface bends downward as you go forward. If your ball moves fast enough sideways, the surface drops away as quickly as the ball drops toward it. That ball never lands. It falls and falls and falls, and the planet keeps curving out from under it. That is orbit. That is what the space station is doing. That is what every satellite, every moon, every planet is doing. Falling forever and missing. Astronauts inside the station are doing the same thing. The station is falling around Earth at about 17,500 miles per hour. The astronauts inside are also falling at that speed. They are not pressing against the walls because the walls are falling with them. There is no floor to push back, nothing to resist. Their bodies do exactly what bodies are supposed to do in curved space-time. They glide. Now here is the part that breaks people's brains. Astronauts are in a permanent state of free fall. the same state your body wants to be in right at this moment. The only difference is that you have a planet getting in your way. They do not. They have already gone around it. If you could fall fast enough sideways from your living room window, you would never hit the lawn. You would simply circle the entire Earth and end up back at your window an hour and a half later. The reason this does not happen is air. The atmosphere would burn you to vapor long before you completed the loop. Astronauts cheat by going above the air, where the orbit can continue without resistance. This is why their feeling of weightlessness is not the absence of gravity. It is the presence of pure, uninterrupted gravity. They are experiencing what gravity actually does when nothing blocks it. Their bodies are moving along the natural curve of space-time, drawn by the same warp that drew the moon into its orbit billions of years ago. If gravity were truly gone up there, the station would not be circling Earth. It would shoot off in a straight line into the dark. Something keeps bending its path, and that something is not a force. Newton looked at a falling apple and saw a force. Einstein looked at the same apple and saw something stranger. He saw geometry doing what geometry does. He saw the apple moving in a straight line through a universe that was no longer flat. For 200 years, the world believed Newton. Every object in the universe pulls on every other object with an invisible force that reaches across empty space. The sun grabs Earth. Earth grabs the moon grabs the oceans and makes them rise. This force, this gravity was treated like a thread connecting every massive thing to every other massive thing. Pull on one end and the other end answers. It worked. The math was clean. The predictions matched the planets. Engineers used it to launch rockets and chart comets. For most of human history, this was the truth of how the cosmos held itself together. Then Einstein noticed something Newton never explained. The force of gravity, in Newton's theory, traveled instantly. Move the sun, and Earth feels the change in the very same moment, no matter how far apart they are. That cannot be right. Nothing in the universe travels infinitely fast. The speed of light is the universal speed limit, and Newton's gravity broke it without apology. Einstein replaced the thread with something else entirely. He said there is no force. There is no invisible pull. There is only the shape of space and time. And that shape is decided by what is in it. Mass and energy bend the geometry around them. Bigger mass, bigger bend. The sun creates a deep, wide warp in space-time. Earth creates a smaller one. You create a warp so tiny that no instrument on the planet could ever detect it. Objects moving through this warped geometry do not feel a force pulling them. They simply follow the natural curve of the landscape they live in. A planet orbiting the sun is gliding along the easiest path through warped space-time, the same way a marble rolling across a tilted bowl curves toward the bottom without anything pushing it sideways. The word physicists use for these natural paths is geodesic. A geodesic is the straightest possible line in a curved space. On a flat sheet of paper, the straightest line is what you would expect, a ruler line from point to point. On the surface of a globe, the straightest line is an arc. Fly from New York to Tokyo, and your plane sweeps a curved path across the planet. That curve is the straightest route possible on a sphere. The plane is not turning. The world beneath it is. This is what every falling object is doing. It is moving in a straight line through curved space-time. From outside, the path looks bent. From the object's point of view, nothing strange is happening at all. It is simply going forward. The implications are staggering. Gravity is not something objects do to each other. Gravity is what space and time do when matter and energy are present. The universe is shaped by what it holds, and what it holds is guided by its shape. Matter tells space-time how to curve. Curved space-time tells matter how to move. 2 sentences, 2 ideas. They replaced Newton, and once you accept that gravity is geometry, the next question becomes impossible to ignore. If nothing is pulling on a falling apple, then what exactly is happening when it drops? Drop a coin from your hand, it falls, it speeds up, it hits the floor, Newton said the Earth pulled it down with a force called gravity. Einstein said the coin was going perfectly straight the entire time. Both cannot be right, and Einstein has won every test for over a century. Here is the strange truth. A falling object is not accelerating in any real sense. Inside the coin's own experience, no force acts on it. No tug, no pressure. It feels weightless, the same way an astronaut does in orbit. If you could shrink yourself down and ride along with that coin from your hand to the floor, you would feel nothing at all. No wind in the sense of force. No sensation of dropping. You would simply observe yourself drifting while the floor rushed up to meet you. The acceleration we see from outside is real to us because we are standing on a planet whose ground is constantly being pushed upward by the rocks and crust beneath it. The Earth is shoving us up. The coin is doing what the coin wants to do, which is move along its straight path through warped space-time. The collision between the coin and the floor is not the coin being yanked down. It is the floor charging upward into the coin. This sounds insane until you remember the equivalence principle. Free fall is identical to drifting in deep space with no gravity. If a coin in free fall feels nothing, then nothing is acting on it. Nothing is pulling it. The coin is simply going forward while the floor accelerates into its path. Imagine you are floating in the middle of empty space, far from any star or planet. Suddenly, a wall comes flying toward you at 30 feet per second. You did not move. The wall moved. When it hits you, you feel the impact. But you were never the one accelerating. That is exactly what happens when an object hits the ground on Earth. According to Einstein, the ground is the wall. You are the floating astronaut. The collision is not gravity grabbing you. It is the planet driving its surface upward. The whole Earth is doing this. Every cubic foot of rock and soil is being pushed outward by the rock beneath it, all the way down to the core. The crust we walk on is the top of a tower of upward push, billions of years old. That is the force you feel in your legs. That is what crushes a coffee cup when it lands. The pull of gravity is silent. The shove of the ground is loud. This idea changes the entire meaning of the word fall. Falling is not motion caused by a force. Falling is the absence of being pushed. The only objects in the universe truly at rest, in a deep physical sense, are the ones in freefall. Sitting in a chair is not rest. It is constant acceleration upward, pressed against the floor of a planet that refuses to let you do what your body naturally would. Right now, your skeleton is being shoved against your skin by a chair that is being shoved against your bones, by a building that is being shoved upward by Earth itself. The pressure travels through every layer beneath you, miles deep, until it reaches the heart of the planet, where the push begins. You are not heavy. You are being held still. In 1907, a young patent clerk sat at his desk in Bern, Switzerland, sorting through paperwork about electric devices. His name was Albert Einstein. He was 28 years old, and he was about to have an idea that would dismantle 200 years of physics. He later called it the happiest thought of his life. The thought was simple. If a person falls freely, he will not feel his own weight. That was it. One sentence. A man falling from a roof would, in the brief moments before impact, feel weightless. His body would experience nothing. He could empty his pockets and the coins would float beside him. He could let go of his hat and it would drift, motionless, in front of his face. To him, in that falling room, gravity would have vanished. This struck Einstein like lightning because it meant something profound. The sensation of weight, the thing we call gravity, was not a permanent property of the universe. It was a feature of being blocked from falling. Take away the block and the feeling disappears. He pushed the idea further. He imagined a man in a sealed elevator with no windows. The elevator is far out in deep space, drifting between the stars, with no gravity nearby. Suddenly, an invisible cable yanks the elevator upward at 32 feet per second squared, exactly the rate at which objects fall on Earth. Inside the elevator, The man feels his feet press against the floor. He feels his body grow heavy. If he drops his keys, they crash to the ground at his shoes. He has no idea he is in space. He thinks he is standing in a perfectly ordinary room on a perfectly ordinary planet. Einstein realized something staggering. There is no experiment the man can perform inside that sealed elevator to tell the difference. Acceleration through empty space and standing on the surface of a planet produce identical results in every measurable way. They are not similar, they are the same. This was the equivalence principle, and from this single idea, Einstein built an entirely new theory of gravity. If acceleration and gravity are indistinguishable, then gravity itself might be a kind of acceleration, not an acceleration in the ordinary sense, an acceleration built into the geometry of space and time. A warping so deep that motion through it produces the same sensation as being pushed by a rocket. This is the core of general relativity. Every massive object in the universe, every star, every planet, every grain of sand bends the fabric of space-time around it. Objects moving through that warped fabric appear to be accelerating, even though from their own point of view, they are not. They are simply gliding along the natural shape of the space they live in. The man in the falling elevator is not weightless because gravity has stopped acting. He is weightless because he is now moving along the natural curve, with nothing in his way. The man in the rising elevator feels heavy not because gravity has been turned on, but because the floor is shoving him into a path he would not have taken. It took Einstein 8 more years to work out the mathematics. 8 years of struggle, of dead ends, of pages of equations covered in his own corrections. When he finished in 1915, he had a theory that explained gravity better than Newton ever did. And the first thing it predicted was something Newton's theory could not even imagine. In 1589, a young Italian named Galileo Galilei climbed to the top of the Leaning Tower of Pisa. The story may be partly legend, but the experiment is real. He dropped 2 cannonballs from the top. One was heavy, one was light. Aristotle had taught for nearly 2,000 years that heavier objects fall faster. Common sense seemed to agree. A rock falls faster than a feather. Everyone knew this. Both cannonballs hit the ground at the same time. Air resistance changes things for a feather. Without air, a feather and a hammer fall at exactly the same rate. This was famously proven in 1971, when astronaut David Scott stood on the airless surface of the moon and dropped a real hammer and a real falcon feather. They landed together. The video still exists. You can watch it. Both objects, despite weighing wildly different amounts, hit the lunar dust at the same instant. This fact is one of the strangest in all of physics, and Newton could never fully explain it. In Newton's theory, the force of gravity on an object depends on its mass. Heavier things feel a stronger pull, but heavier things are also harder to move. A bowling ball is harder to push than a tennis ball, no matter what you do to it. The resistance to being moved is also called mass. And here is the puzzle that haunted physicists for centuries. The mass that determines how strongly gravity pulls on you and the mass that determines how hard it is to push you are exactly the same number. There is no reason in Newton's universe why they should be. Gravity could have pulled twice as hard on something while still requiring the same effort to move. The universe could have been built that way. It was not. The 2 kinds of mass match to a precision better than 1 part in a trillion. Why? Newton shrugged. He had no answer. He simply wrote the law and moved on. It worked, even if no one knew why. Einstein gave the answer. There is no force pulling on the cannonballs. There is no force pulling on the hammer or the feather. All objects in freefall are moving in a straight line through curved space-time. They are not accelerating in any real sense. They are gliding, and every object glides the same way through the same geometry, regardless of what it is made of or how much it weighs. It is like asking why 2 cars rolling down the same hill take the same path. They take the same path because the hill is the same. The hill does not care what the cars weigh. The hill is just a hill. Gravity does not care what objects weigh, because gravity is not a force grabbing them. Gravity is the shape of the road. All travelers on that road follow the same curve. This explains why a feather and a hammer fall together in a vacuum. They are not being pulled by gravity at all. They are simply free of resistance, free to follow the natural geometry around them. The Earth bends space-time in a particular way, and any object placed in that warp glides along the same curve. Astronauts in orbit demonstrate this every second of every day. Their entire bodies, all their tools, every screw and pen and microchip, all of it falls together in perfect synchrony around the planet. They do not drift apart from their equipment. They drift together, because the curve is the same for everyone. And once you accept that gravity bends past through space, the next discovery becomes inevitable. Gravity must also bend something else. The clock on your wrist runs slower than the clock on your bookshelf above it. Not by much, not enough to notice. But the difference is real, and it has been measured in laboratories more times than anyone can count. Time itself runs slower the closer you are to the ground. This sounds like a parlor trick. It is not. It is one of the most thoroughly tested predictions in all of science. In 2010, physicists at the National Institute of Standards and Technology in Colorado built 2 atomic clocks of stunning precision. They placed one on a table. They raised the other by about 1 foot. The higher clock ticked faster. The difference was tiny, billionths of a billionth of a second per day, but it was unmistakable. 1 foot. That is all it takes for time to drift apart. The reason is gravity, or rather, the reason is the curved geometry of space-time that we call gravity. Mass bends time as well as space. The closer you are to a massive object, the deeper you sit in the warp, and the slower your clock runs compared to clocks farther away. The Earth bends time around itself like a soft funnel. The bottom of the funnel is the planet's core. The top is empty space. Every height in between has its own rate of time. Your head, right now, is aging faster than your feet. Microscopically, immeasurably, but truly. Over an entire human lifetime, the difference adds up to a few billionths of a second. A heartbeat, or 2, not enough to matter for you, but the principle is enormous. Think about what this means. Time is not a universal river flowing at the same speed everywhere. There is no master clock ticking out the seconds of the cosmos. Each region of space has its own pace. Mountains tick faster than valleys. Airplanes tick faster than the ground beneath them. Satellites tick faster than airplanes. And the deeper you go, the slower it gets. If you could stand on the surface of a neutron star, where gravity is unimaginably strong, your clock would crawl. A second to you would stretch into far longer for someone watching from a safe distance. If you stood at the edge of a black hole, time would slow so dramatically that you could spend what felt like an hour there and return to find that millions of years had passed on Earth. The movie Interstellar showed this with one of its most haunting scenes. A planet orbiting close to a supermassive black hole made every hour on its surface equal to 7 years on the home ship. That sequence was not science fiction. Or rather, the physics was not. The setup was extreme but mathematically accurate. Time really does behave this way. Even here on Earth, the effect is detectable. A clock at the base of Mount Everest ticks slightly slower than a clock at the summit. A scientist working in a basement laboratory ages slightly slower than a colleague on the top floor. None of this is metaphor. None of it is approximation. It is the real measured behavior of time in a gravitational field. The strange thing is how casual the universe is about it. There is no machinery to slow time down, no invisible gears grinding deeper near massive objects. The geometry of space-time simply allows it. Bend space, bend time, the same way you cannot rotate one without affecting the other. And once engineers realized that time really does run at different rates in different places, they faced a problem, a practical problem, because we had just launched a network of clocks into the sky. Pull out your phone, open a map, watch a blue dot find you on the planet within seconds. That blue dot is a small miracle, and it is also a lie. To get your position right, your phone has to talk to satellites that tick at a different rate of time than you do. If engineers had ignored Einstein, that blue dot would drift by miles every single day. The Global Positioning System uses a fleet of satellites orbiting about 12,000 miles above Earth's surface. Each satellite carries an atomic clock of staggering precision, accurate to billionths of a second. The system works by measuring how long it takes signals to travel from the satellites to your phone. The phone compares the timing from several satellites at once and triangulates your position. The whole thing rests on one assumption: the clocks must agree. They do not. The clocks on those satellites run faster than the clocks on the ground. Two effects fight over the timing. First, the satellites are moving fast, around 8,000 miles per hour, and special relativity says fast-moving clocks tick slower. By that rule alone, the orbiting clocks lose about 7 millionths of a second per day, but the satellites are also high above Earth in a weaker region of curved space-time. General relativity says clocks in weaker gravity tick faster. By that rule, the satellites gain about 45 millionths of a second per day. Subtract the two effects. The net result is that satellite clocks run roughly 38 millionths of a second faster every day than identical clocks on the surface. 38 millionths of a second sounds harmless. It is not. Light travels nearly a foot in 1/1000th of a second. Multiply that out, and the position error grows by about 7 miles per day. Within a single day of operation, your phone would think you were standing in a different city. Within a week, you would be on the wrong side of the country. The entire system would collapse into nonsense. Engineers solved this by deliberately offsetting the satellite clocks before launch. Each clock is tuned to tick at a rate that looks wrong on the ground, but becomes perfectly correct once the satellite reaches orbit. They are slowed down by exactly the amount Einstein predicted, so that from your phone's point of view, every clock in the sky agrees. This is one of the cleanest demonstrations of general relativity in everyday life. Every time you check directions, every time a rideshare app finds your driver, every time an airliner lands using satellite guidance, you are relying on the assumption that gravity bends time. Without that correction, modern navigation would not function. There is something poetic in this. For most of human history, gravity was the thing that made apples fall. By the late 20th century, it had become a quiet partner in every commute, every delivery truck, every search and rescue operation. Einstein's equations were no longer the playground of theorists. They were running silently in chips the size of a fingernail in millions of pockets around the world. The first GPS satellite to carry an atomic clock launched in 1977. The engineers were so uncertain about whether the relativistic effects would really matter that they built the satellite with a switch. The clock could be corrected, or it could run uncorrected depending on what the data showed. When they finally turned the correction on, the system worked. When it was off, the system failed exactly as predicted. Einstein had been dead for over 20 years. The clocks proved him right. And the next prediction would require listening to the universe itself. If the sun vanished right now, you would not know it for over 8 minutes. Earth would keep orbiting nothing. Plants would keep photosynthesizing. Birds would keep flying. The sky would still be blue. Then, 8 minutes and 20 seconds later, the sunlight would cut out, the temperature would begin to plunge, and Earth would suddenly drift off in a straight line into the cold. This is one of the strangest consequences of general relativity. Gravity does not act instantly, it travels. And it travels at exactly the speed of light. No faster. Newton would have disagreed. In his universe, gravity reached across empty space without delay. If you moved a star, every planet in the galaxy felt the change in the same instant, no matter how far away. The pull was assumed to be instantaneous, a kind of invisible hand that touched everything at once. This worked well enough for predicting orbits, but it broke a deeper rule of nature. The universe has a speed limit. Nothing can transmit information faster than light. Not radio signals, not electric fields, not magnetic forces, and, as Einstein realized, not gravity. If the sun were to suddenly disappear, Earth would have no way of knowing for the same reason it would have no way of seeing it. The information about the change must travel across the gap, and that information moves at the same finite speed as a photon. This means gravity is not a static pull. It is a signal. The sun is constantly broadcasting its gravitational influence outward, and that broadcast washes over Earth 8 minutes after leaving the sun's surface. The light you see in the sky right now left the sun 8 minutes ago. The gravitational tug holding Earth in orbit also left the sun 8 minutes ago. Both arrive at the same time. Both carry the same news. Imagine a swimmer thrashing in the middle of a still pond. The ripples spread outward in slow, expanding rings. A leaf floating 10 feet away does not bob until the ripples reach it. The same is true of every massive object in space. When something shakes, when something accelerates, when something moves violently, ripples in the curvature of space-time spread outward at light speed. Distant objects only feel the change once the ripple arrives. This is why physicists sometimes call gravity a wave phenomenon, even though we usually picture it as a steady pull. The steadiness is an illusion of stillness. The sun is not changing rapidly, so its gravitational field looks frozen, but it is constantly being refreshed by signals leaving the sun at light speed. A snapshot taken now is a snapshot of 8-minute-old news. This has staggering consequences for cosmic events. When a star explodes as a supernova, the matter around it does not instantly feel the loss. A planet 10 light-years away will keep orbiting the explosion as if nothing happened for an entire decade. Then, in the same moment the light arrives, the gravitational change arrives too. Both signals run side by side. When something truly violent happens in the cosmos, like two black holes spiraling into each other, the gravitational ripples produced are intense enough to be detected from billions of light-years away. They cross the universe at the speed of light, gradually weakening, until they wash over Earth and shake our most sensitive instruments by amounts smaller than an atom. We have seen this happen. We have caught the ripples. But before we get to that miracle, there is a more immediate puzzle worth sitting with. Because if the sun went out right now, you would still feel its pull, and that strange grace period would only last 8 minutes. Imagine that at this precise second, somewhere in another galaxy, an alien civilization aims a weapon of impossible power at our sun and erases it from existence. No explosion, no flash, no debris. The sun simply ceases to be. What happens next on Earth? For the first 8 minutes and 20 seconds, absolutely nothing. The sky stays blue. The sunlight keeps streaming through your window. Trees keep producing oxygen. Birds keep flying. Tides keep rolling against beaches. Earth continues circling the spot where the sun used to be, as if nothing had happened. Your heart beats normally. Your phone still pings. Civilization does not even hiccup. This is because both light and gravity travel at the same speed, and that speed is finite. The last image of the sun is still racing across the solar system. So is the last gravitational tug. Earth continues to follow the orbit that was set by a sun that already does not exist. At the 8-minute 20-second mark, two things happen at once. The sunlight ends. The sky does not slowly fade. It simply goes black, faster than any sunset. The sun blinks out of the sky like a switch being flipped. And at that exact same instant, Earth feels the absence of the sun's gravity. The invisible warp in space-time that has been holding Earth in a gentle curve for over 4 billion years suddenly relaxes. Earth does not fall. Earth does not get sucked anywhere. There is nothing left to fall toward. Instead, Earth does what every object in space wants to do when nothing is bending its path. It moves in a straight line. Whatever direction Earth was traveling in the moment the sun disappeared, that is the direction Earth keeps going. Forever, until something else gets in the way. The speed Earth was moving when the Sun vanished is about 67,000 miles per hour. That is the orbital velocity Earth has built up over billions of years of being gently bent by the Sun's gravity. Without the bend, that speed becomes a straight line. Earth becomes a planet-sized bullet, fired out of the solar system on a tangent. The other planets do the same thing, each at their own 8-minute delay relative to their distance from the Sun. Mercury feels the change first, in about 3 minutes. Then Venus, around 6. Then Earth. Then Mars, around 12 minutes. Then the outer giants, each in their own time. One by one, the entire solar system unspools into the darkness, every planet flying off in whatever direction it happened to be moving when the news arrived. Within hours, Earth's temperature begins to plunge. The atmosphere starts to chill rapidly. Within days, the oceans begin to freeze over. Within weeks, the planet becomes a frozen rock racing through interstellar space. Plant life dies. Most animal life follows. The deepest parts of the ocean, kept warm by the planet's internal heat, might harbor strange survivors for a long time, but the world humans knew is gone. The point of this thought experiment is not the apocalypse. The point is what it reveals about gravity. Gravity is not glue. It is not a string connecting the Sun to its planets. It is a signal broadcast through the geometry of spacetime, moving at the cosmic speed limit. Cut off the broadcast, and the connection dies as the last wave passes. This is also why we cannot warn the Sun about our existence faster than light. Whatever Earth does, the Sun will not feel it for over 8 minutes. The cosmos has rules. Even gravity must obey them. And once you accept that gravity is a slow-traveling signal, the next mystery becomes the question of what it actually does to objects in its path. Mercury was the planet that broke Newton. For 200 years, Newton's law of universal gravitation predicted the orbits of every planet with breathtaking accuracy. Astronomers used it to find Neptune before anyone had ever seen Neptune through a telescope, because something was tugging on Uranus in just the right way. Newton's math was the language of the solar system. Then there was Mercury. Mercury's orbit is not a perfect circle. No planet's orbit is. Every planet traces an oval, with the Sun slightly off-center. Mercury, the closest planet to the Sun, has the most elongated oval of the group. And there is one strange feature of this oval that puzzled astronomers for over a century. The oval itself slowly rotates. Imagine drawing a stretched ellipse on a piece of paper, then rotating the whole paper by a tiny angle every year. That is what Mercury's orbit does. The long axis of the oval slowly swings around the Sun. Astronomers call this precession. Every planet's orbit precesses to some degree, and Newton's gravity can explain most of it. The pulls from the other planets, especially Jupiter, gently tug on the orbit and cause it to drift over millennia. But when astronomers in the 1800s did the math for Mercury, they found something disturbing. The orbit was precessing faster than Newton's theory allowed. Not by much, by a tiny amount. About 43 arcseconds per century, that is less than 1/50th of a degree every 100 years. But it was real, and it would not go away. For decades, scientists searched for explanations. Maybe there was an undiscovered planet even closer to the Sun, pulling on Mercury. They called it Vulcan. They searched for it with telescopes. They never found it. Maybe the Sun had a bulge that affected the orbit. The bulge was too small. Maybe some unknown asteroid belt was responsible. There was no such belt. Newton's gravity could not explain Mercury. The math simply refused to match the sky. In 1915, Einstein finished his theory of general relativity. One of the first things he did was apply it to Mercury. He did not need to invent new planets. He did not need bulges or asteroids. He simply calculated how Mercury would move through the curved space-time around the Sun. The Sun's mass warps the geometry of its surroundings, and Mercury, being closest, swims through the deepest part of that warp. When Einstein worked out the math, the extra precession appeared naturally. Exactly 43 arcseconds per century. Not approximately, exactly. The number matched the observed discrepancy with stunning precision. Einstein later wrote that when he saw the calculation work, his heart pounded. He felt physically ill from the excitement. For days, he could not focus on anything else. He had taken the most stubborn puzzle in solar system astronomy, a puzzle that had defeated the best minds for half a century, and dissolved it with a single new idea about the shape of space. This was the first major confirmation of general relativity. Other tests came later, more dramatic and more public, but Mercury was the planet that whispered the truth first. It was the canary that no one had heard properly until Einstein arrived. The reason Newton's gravity failed for Mercury is the same reason it works almost everywhere else. Newton's law is an excellent approximation in weak gravitational fields. The closer you get to a massive object, the more space-time curves and the more Newton's approximation breaks down. Mercury, sitting closest to the Sun, lives where the curvature is steepest. It feels the geometry that more distant planets barely notice. And if curved space-time could bend the path of a planet, it could surely bend something else, something that has no mass at all. A photon has no weight. It is pure energy racing through the cosmos at 300 million feet per second times nearly 10, with nothing to pull on, nothing to grip. Newton's law of gravity says that the force between two objects depends on their masses. Take away the mass, and the force should not feel gravity at all. Newton was wrong. Light bends around massive objects. Stars deflect starlight passing near them. Galaxies deflect light from galaxies behind them. The deeper the warp in space-time, the sharper the bend. This is not a force gripping the photon. It is the photon following the only path available to it in a region where the geometry has been twisted. The reason becomes clear once you understand that gravity, in Einstein's picture, is not about mass alone. It is about the curvature of the road. Light, like everything else, must travel along whatever shape space-time takes. If the road bends, the light bends with it, even though no force is acting on it. The photon is moving in a straight line through a space that itself is curved. The first major confirmation of this came in 1919. 4 years after Einstein published general relativity, a British astronomer named Arthur Eddington led an expedition to a remote island called Principe, off the western coast of Africa. He was waiting for a total solar eclipse. During the eclipse, the moon would block out the sun's blinding light, and the stars normally hidden behind the sun's glare would briefly become visible. Einstein had predicted that starlight passing close to the sun would be deflected by a specific, measurable amount. The light would bend as it skimmed the sun's edge, and the apparent position of the background stars would shift by a tiny angle. If you photographed those stars during the eclipse and compared the photos to images of the same stars at night, 6 months later, when the sun was on the other side of Earth, the stars would appear to have moved. The amount of the shift would be the test. Eddington took the photographs. He waited for clouds to clear. He made his measurements. And when the analysis was done, the stars had moved by exactly the amount Einstein had predicted, twice as much as Newton's old theory would have allowed if light had a tiny effective mass. The deflection matched the geometric prediction of curved space-time perfectly. The news exploded across the world. Einstein woke up famous. Newspapers ran headlines declaring that the laws of physics had changed. A young patent clerk had overthrown the cosmic order built by Isaac Newton centuries earlier. Einstein became, almost overnight, the most recognizable scientist on Earth. The reason this confirmation was so powerful is that it required no excuses. There was nothing to fudge. The photographs either showed the predicted shift or they did not. And from that moment on, light was understood to be part of the gravitational story. Every photon racing across the cosmos right now is bending slightly as it passes near stars and planets and galaxies. The light from distant suns reaches our eyes not in perfectly straight lines, but in subtly curved paths shaped by every massive object it has passed. The night sky you see is, in a small way, a distorted image. Most of the time, the distortion is invisible. The objects between Earth and a distant star are usually not massive enough to cause a bend you would notice. But sometimes the geometry lines up just right, and the universe puts on a show that no human imagination could have prepared us for. Sometimes, the bending becomes a lens. When a galaxy sits perfectly between you and another galaxy far behind it, something extraordinary happens. The light from the background galaxy curves around the foreground galaxy on every side, like water flowing around a stone in a stream. From your point of view, the distant galaxy is no longer a single point of light. It becomes a ring, a circle of light wrapped around an empty space at the center. These are called Einstein rings. They are some of the most beautiful objects in the visible universe. The Hubble Space Telescope and the James Webb Space Telescope have captured dozens of them, each one a delicate halo of warped starlight surrounding a foreground galaxy. They look unreal. They look painted. They are not. They are pure geometry, drawn by the warping of space-time itself. The physics is straightforward, once you accept that gravity bends light. Imagine a flashlight shining directly at your eye from 100 miles away. Now place a heavy lens between you and the flashlight. The light from the flashlight does not travel in a straight line to your eye anymore. It spreads out, hits the lens, and gets bent. If the lens is perfectly aligned with the flashlight and your eye, the light bends around all sides of the lens equally. What you see is not a single point of light, but a circle of light surrounding the lens. Replace the flashlight with a distant galaxy. Replace the lens with a massive foreground galaxy. The geometry is the same. The result is an Einstein ring. For the ring to form perfectly, the alignment must be nearly exact. A slight misalignment turns the ring into an arc. A larger misalignment splits the image into multiple copies of the background galaxy, scattered around the foreground lens like the smeared reflections in a funhouse mirror. Astronomers have seen all of these effects in real photographs. They have catalogued thousands of cases where a foreground galaxy has produced multiple distorted images of objects behind it. This phenomenon is called gravitational lensing. It is now one of the most powerful tools in astronomy. By measuring how much the background light is bent, scientists can weigh the foreground galaxy without ever touching it. They can map its mass. They can even detect mass that emits no light at all. This is how dark matter was first inferred to be present in such enormous quantities. The visible stars in galaxies do not weigh enough to produce the lensing effects we see. Something else is there, something invisible, contributing most of the gravity. The lensed light is bent more than it should be, if only the glowing matter were responsible. Whatever is causing the extra bend, it makes up roughly 5 times more mass in the universe than all the stars and gas combined. We do not know what dark matter is. We only know that the geometry around galaxies bends light, as if there is far more mass present than we can see. Gravitational lensing also lets astronomers see things they could never see otherwise. A faint, distant galaxy can be magnified by a foreground galaxy's lensing effect, making the background object visible to telescopes that would otherwise miss it entirely. The universe sometimes provides its own zoom lens, and astronomers have learned to look for the magnified images these natural lenses create. The first Einstein ring ever photographed was discovered in 1987. Since then, the number has grown into the hundreds. Each one is a confirmation. Each one is a small monument to the man who, sitting in a patent office in Bern, imagined that space and time were not the stage, but part of the play. The light that makes those rings has been traveling for billions of years. It survived every twist and turn of cosmic geometry, and then it ran into something even more extreme, a ripple in space itself. Throw a stone into a pond. Ripples spread outward in expanding rings, each one a small disturbance in the surface of the water. Now imagine that the pond is not water, it is space itself. The stone is not a stone, it is 2 black holes spiraling toward each other at nearly the speed of light. The ripples are not made of water, they are made of warps in the geometry of the cosmos. These are gravitational waves. Einstein predicted them in 1916. For nearly 100 years, no one could prove they existed. The waves were thought to be far too weak to ever detect. A passing gravitational wave stretches and squeezes space by amounts smaller than 1,000th the width of a proton. To catch one, you would need an instrument capable of measuring distances with an accuracy beyond anything ever built. Humans built one anyway. Every massive object in the universe that accelerates produces gravitational waves. You produce them when you wave your arm. The Earth produces them as it orbits the Sun. The waves your body generates are so faint that no instrument will ever detect them. Even Earth's orbital waves are vanishingly small. To create gravitational waves strong enough to cross the universe and be measurable on the other side, you need cataclysmic events, black holes colliding, neutron stars merging, supernovas tearing themselves apart. When something violent enough happens, the ripples spread outward across space-time at the speed of light. They pass through everything. They do not weaken much over distance because they are not light being absorbed. They are the very stage being shaken. Walls do not stop them. Planets do not stop them. They pass through Earth as if Earth were not there. But they leave traces, tiny ones. A passing gravitational wave will momentarily stretch space in one direction while squeezing it in the perpendicular direction. If you had a perfectly square room and a strong enough wave passed through it, the room would briefly become slightly rectangular. Then it would return to square. Then it would become rectangular in the other direction. The cycle repeats as the wave passes by. The amount of stretching is unimaginably small. For a wave from a black hole merger a billion light-years away, a 1-mile-long instrument would change in length by about 1,000th the diameter of a proton. That is roughly 1 part in a sextillion. To detect that, you need lasers more stable than anything in nature, and mirrors hung from threads in vacuum chambers, so quiet that distant traffic can ruin the measurement. The instrument is called LIGO. It stands for Laser Interferometer Gravitational Wave Observatory. There are 2 of them in the United States, one in Washington and one in Louisiana, plus a third in Italy called Virgo, and a fourth in Japan called Kagra. They are spread across the globe so that when a wave is detected, scientists can compare the timing at different locations and figure out where in the sky the wave came from. Each LIGO detector is a giant L-shaped tube 2.5 miles long on each arm. A laser beam is split and sent down both arms. The light bounces off mirrors at the ends and returns. When the beams recombine, any tiny difference in the lengths of the 2 arms shows up as a change in the light's interference pattern. If a gravitational wave passes through, one arm gets slightly longer while the other gets slightly shorter, and the pattern shifts. For decades, LIGO operated and detected nothing. The instrument was upgraded. The sensitivity grew. The teams waited. And then, on a quiet September morning in 2015, the universe finally spoke. On September 14, 2015, at 5:51 in the morning Eastern Daylight Time, a signal arrived at the LIGO detector in Livingston, Louisiana. 0.007 of a second later, the same signal arrived at the LIGO detector in Hanford, Washington. The 2 instruments, separated by nearly 2,000 miles, had both picked up an identical pattern. The tiny lengths of their laser arms had wobbled by amounts no instrument in human history had ever measured. A gravitational wave had washed over Earth. The signal lasted about 0.2 of a second. In that brief stretch of time, the LIGO detectors recorded a rising chirp, a smooth swelling pattern that climbed in frequency before cutting off sharply. To the scientists watching the data, it looked exactly like what their models predicted for 2 black holes spiraling into each other and merging. It took weeks to be sure. The team double-checked everything. They tested the data against possible interference. They considered every artifact, every glitch, every cosmic ray. The signal held up. It was real. On February 11, 2016, the LIGO scientific collaboration announced to the world that Einstein's prediction had been confirmed. Gravitational waves were not theory anymore. They were observation. The event that produced the wave had happened over 1 billion years ago, in a galaxy so distant that human civilization could not be glimpsed from anywhere near it. Two black holes, one weighing about 36 times the mass of our Sun, the other about 29, had been locked in a death spiral for an enormous amount of time. They had circled each other faster and faster, drawing closer with every revolution. In the final fraction of a second before merging, they were whipping around at close to the speed of light. When they collided, they became a single larger black hole weighing about 62 solar masses. The remaining 3 solar masses, an amount equal to 3 entire suns, was converted directly into gravitational waves and radiated outward into the cosmos. The energy released in that final moment was greater than the combined light output of every star in the observable universe, all at once. But none of it was light. All of it was rippling space-time. For over 1 billion years, the waves traveled outward, spreading and weakening. They crossed empty space, distant galaxies, clouds of gas, regions of dark matter. They washed through our own galaxy. They passed through Earth. They passed through your great-grandparents' parents, and through every living thing on the planet at the time. They were too faint to feel, too faint to notice, too faint to detect with anything humans had built before. LIGO caught them. The mirrors at the end of the laser arms moved by about 1,000th the width of a proton. To put that in scale, a proton is about 1/1,000,000th of 1/1,000,000th of an inch across. 1,000th of that is the level of motion LIGO measured. The fact that any instrument could detect such a tiny shift is itself one of the most remarkable engineering achievements in history. Since that first detection, LIGO and its partners have caught hundreds of similar events. As of recent observing runs, the network has logged around 300 black hole mergers and a handful of neutron star collisions. The universe, it turns out, is full of these violent encounters. Every few days, somewhere out there, 2 of the densest objects in nature finish their long dance and become one. We have only been listening for a decade. The catalogue is growing fast, and one of the loudest things we ever heard came from a collision that defied every model we had. If you slow down the LIGO signal from that first detection and convert it to sound, you can hear it. It does not sound like much. A short, low warble that climbs into a higher pitch and then suddenly stops, less than 1/4 of a second long, less interesting than a dog's bark. But that little chirp is the loudest moment in the history of physics. The chirp is the sound of 2 black holes finishing their billion-year spiral. The rising pitch corresponds to their accelerating orbit. As they drew closer, they whipped around each other faster, and the gravitational waves they produced rose in frequency. The sudden cutoff is the moment they merged. After that, the combined black hole settles into stillness, and the ripples fade. Scientists call this pattern a chirp because it really does sound like one. The bird call shape of the signal is so recognizable that even untrained ears can pick it out of background noise. Every black hole merger produces a chirp of some kind, varying in pitch and duration depending on the masses involved. Heavier black holes produce slower, lower chirps. Lighter black holes produce faster, higher ones. By analyzing the shape, physicists can read out the masses, spins, and distance of the event. The first chirp came from black holes, of about 36 and 29 solar masses. Other chirps have come from much bigger objects. In late 2023, LIGO and its partners detected a signal called G2231123. The 2 black holes involved weighed about 100 and 140 times the mass of the Sun. They merged into a single black hole of around 225 solar masses. That single event released more raw power than the combined light of every star in the observable universe. This was the most massive black hole merger ever detected, and it broke models. Most theories of black hole formation say that black holes between roughly 60 and 130 solar masses should not exist. Yet here were two of them, smashing together to make a much larger one. The leading explanation is that these were second-generation black holes. They were themselves the products of earlier mergers, recycled in environments dense enough to push them back together. Each new detection is rewriting what we know about how black holes form and where they live. Some are in dense star clusters. Some seem to be drifting in regions no one expected. The catalogue of mergers is becoming a census of the dark population of the universe. There is something else worth pausing on. Every one of these chirps confirms Einstein's theory again. The shape of each waveform matches the predictions of general relativity with stunning precision. The math written down in 1915 with a fountain pen in a Berlin apartment predicts the exact pattern of ripples that black holes produce when they collide. Even when those black holes are over 1 billion light-years away and weigh as much as small galaxies, there is a poetic detail to add. The LIGO instruments did not just hear that first signal, they timed it. The 7,000ths of a second delay between the Louisiana and Washington detections told them the direction the wave had come from. It told them where in the sky to look. There was nothing to see, because black hole mergers do not produce light, but the geometry of the heavens had been mapped by an event entirely invisible to the eye. For most of human history, astronomy meant looking at light, stars in the sky, telescopes that gathered photons. With LIGO, astronomy gained a new sense entirely. We can now feel the universe. We can detect events that emit no light at all. We can listen to the cosmic darkness. And the darkest object of all happens to live at the very center of our home galaxy. At the center of our galaxy, 26,000 light-years from where you are sitting, there is a black hole. It has a name, Sagittarius A star, and a mass equal to about 4 million suns crushed into a region smaller than the orbit of Mercury. It sits silent at the core of the Milky Way, and every star you see in the night sky is, in some way, dancing around it. For decades, no one knew what was hiding at the galactic center. The region is shrouded in thick clouds of gas and dust that block ordinary light. Visible telescopes saw nothing useful. Then, in the 1990s, two teams of astronomers, one led by Andrea Ghez in California and the other by Reinhard Genzel in Germany, began tracking the motion of individual stars near the galactic core using infrared light, which slips through the dust where visible light cannot. What they saw was astonishing. The stars were whipping around something invisible at speeds of millions of miles per hour. One star, called S2, completed an entire orbit in just 16 years, swooping past the central object at over 17 million miles per hour at its closest approach. By tracking these orbits over decades, the astronomers calculated the mass of whatever they were circling. The answer came back the same every time: 4 million solar masses, compressed into nothing visible. There was only one possible explanation: a supermassive black hole. In 2020, both Ghez and Genzel received the Nobel Prize in Physics for the discovery. 2 years later, in 2022, the Event Horizon Telescope, a planet-sized network of radio dishes working in unison, released the first direct image of Sagittarius A star. The image showed a glowing ring of superheated gas surrounding a perfectly dark circle. The dark circle was the shadow of the event horizon, the point beyond which not even light can escape. That image confirmed what the orbits had already told us. A black hole really does sit at the center of our galaxy, and it is bending space-time around itself so violently that time near its edge crawls almost to a stop. Every clock that strays close to Sagittarius A star ticks more slowly. The closer it gets, the slower it ticks. At the edge of the event horizon, time, from the perspective of someone far away, freezes. A clock falling toward the black hole would appear to slow down and slow down and slow down, never quite reaching the edge. From outside, the clock seems to fade into a permanent stillness. From the clock's own perspective, nothing strange happens. It crosses the boundary normally, in finite time, and continues on. The two views, the outside view and the inside view, are both correct. They simply belong to different observers in different parts of the warped geometry. This is what gravity does at its most extreme. It bends time so severely that two observers can disagree about whether something has happened yet. The flow of moments, which feels so absolute in everyday life, becomes a feature of where you are standing. Sagittarius A star is far from the largest black hole known. Some are billions of solar masses. They sit at the centers of distant galaxies and shape the evolution of everything around them. But ours is closer. Ours is the one our solar system circles. The sun is moving around it right now, at about 500,000 miles per hour, taking roughly 230 million years to complete a single orbit. You are not standing still. You are riding a star around a black hole. And what waits inside that black hole breaks geometry itself. Cross the event horizon of a black hole, and something happens that almost no one outside physics ever hears about. Time and space exchange identities. The direction toward the center of the black hole stops being a place you can choose to go. It becomes the future. You move toward the singularity not by walking, but by waiting. Every second that ticks brings you closer. There is no turning around. There is no going back. The center of the black hole is now your tomorrow. This is the strangest consequence of curved space-time, and it is real. The math is unambiguous. The Schwarzschild solution, the first exact solution of Einstein's field equations, was worked out in 1916 by a German physicist named Karl Schwarzschild while he was serving in the German army on the Russian front. He died a few months later from an illness he caught in the trenches. The geometry he discovered is still the foundation of black hole physics. Outside a black hole, time and space behave the way you expect. You can move forward or backward in space. You cannot move backward in time. Time has one direction, which we call the future. Space has many directions, all open. Cross the event horizon, and the math flips. The radial direction, the line connecting you to the center of the black hole, becomes time-like. The time direction which used to lead from past to future becomes space-like. What this means in practice is that falling toward the center is no longer optional. It is the only thing you can do. You cannot point your spaceship outward and accelerate away from the singularity any more than you can point your life backward and accelerate toward yesterday. Every direction you look inside the black hole, you see the same thing, falling deeper. This is why nothing escapes from inside a black hole, not even light. The reason is not that gravity has become a stronger pull. It is that the geometry has been rearranged so thoroughly that there is no outward direction left. Outward has become past. The future leads inward. Light traveling away from the singularity, in any direction, still ends up at the singularity, because that is where the future lies. The singularity itself is a problem. According to general relativity, all the mass of the black hole is concentrated at a single point of zero size and infinite density. The math gives an answer of infinity, which is physics speak for I do not know. The theory breaks down. Whatever happens at the singularity, general relativity cannot describe it. To understand what really happens there, we would need a theory that combines gravity with quantum mechanics. We do not have one yet. What we do know is what happens during the fall. If you were unlucky enough to fall into a black hole feet first, the gravitational difference between your feet and your head would grow rapidly. Your feet would be pulled toward the singularity more strongly than your head. The result is a process physicists call spaghettification. Your body would be stretched into a long, thin strand, like pasta, before being torn apart at the molecular level. For small black holes, this happens long before you cross the event horizon. For supermassive black holes like Sagittarius A star, the tidal forces at the event horizon are gentle, and you could fall in without being shredded, only to face the same fate deeper inside. The deepest part of the black hole, where the geometry collapses, is the place where our theories run out. It is the wall at the end of physics as we currently know it, and the walls themselves have something strange to say about gravity. The standard explanation of a black hole sounds simple. Gravity is so strong that not even light can escape. It is a clean sentence. It fits in a textbook, and it is misleading. Light does not get pulled back by gravity inside a black hole. Gravity is not a force grabbing photons and yanking them down. What actually happens is that the geometry of space-time closes in on itself. Every possible path leads to the singularity. There is no road out, not because the road is blocked, but because the road does not exist. Imagine a river that flows faster than you can swim. If you jump in, no matter how hard you paddle, you are carried downstream. You can swim sideways. You can struggle. You can use every ounce of strength you have. The current is faster than you, and the river wins. This is a useful image, with one important difference. The river has banks. The river ends somewhere. Inside a black hole, the river is the entire universe, and every direction is downstream. The event horizon is the boundary where the river first becomes faster than light can swim. Outside the horizon, light can still struggle upstream, climbing out of the gravity well, losing energy as it goes. At the horizon, the current becomes exactly as fast as light. Photons can hover there in theory, but they cannot rise. Inside the horizon, the current outpaces light entirely. Even a photon racing outward at the universal speed limit is carried inward faster. There is no force pulling on the photons. The photons are moving in straight lines, as they always do. The geometry has tilted so that every straight line points inward. This is also why the event horizon is called a one-way membrane. From outside, you can see it as a black sphere with a glowing ring of hot gas swirling around it. Light from the surrounding cosmos passes nearby and bends around it. Some light falls into it. None comes out. From inside, the membrane is the past. You cannot revisit the past, so you cannot return to the outside. The horizon is gone behind you, not because it is yesterday. This understanding leads to a strange consequence. The size of a black hole is not measured by what is inside it. It is measured by the surface area of its event horizon. A black hole with more mass has a larger event horizon. A black hole with less mass has a smaller one. The interior is in some sense irrelevant to the outside universe. All that matters is the boundary. All that can be observed is the surface. Stephen Hawking realized in the 1970s that this surface acts like a hot object. It glows very faintly with what is now called Hawking radiation. The radiation is too faint to detect for any astrophysical black hole, but the theoretical existence of the glow tells us something profound. Black holes are not completely black. They slowly leak energy back into the universe. Over enormous stretches of time, they evaporate. A black hole the mass of the Sun would take longer to evaporate than the current age of the universe times 10 to the 64 power. The number is so vast that the word inconceivable is barely strong enough. But the process is real. Even black holes are not forever. And while a black hole is alive, it does something to the space around it that took 50 years to confirm. It twists. A spinning black hole does not just bend space-time, it drags it. The geometry around a rotating mass behaves like honey being stirred by a spoon. The honey gets pulled around with the spoon. The space around the black hole gets pulled around with the spin. Anything caught in the swirl is forced to rotate along with it, whether it wants to or not. This phenomenon is called frame dragging, and it was predicted by two Austrian physicists, Josef Lenz and Hans Thirring, way back in 1918. They worked out the math directly from Einstein's equations and showed that a rotating massive body would twist the geometry of its surroundings. For 100 years afterward, the prediction sat untested. Earth rotates too slowly to produce a significant effect, and no one had built an instrument sensitive enough to measure it. Then came Gravity Probe B, launched by NASA in 2004. This satellite carried 4 perfectly polished spheres of fused quartz, each coated in a thin layer of metal, each spinning at thousands of revolutions per second. These spheres were the most spherical objects ever manufactured by human hands. If they had been the size of Earth, the tallest mountain on their surface would have been about 8 feet high. They were that smooth. The idea was simple. Spinning objects, like tiny gyroscopes, want to keep pointing in the same direction. If you started top spinning while pointing it at a distant star, it should keep pointing at that star forever, as long as nothing disturbs it. But Einstein's theory predicted that as the gyroscopes orbited Earth, the rotating mass of the planet below would slowly drag space-time around with it. The gyroscopes, sitting in that dragged space, would have their pointing direction gradually twisted away from the star. The effect was tiny, about 1/10 of an arcsecond per year. That is about 36,000 times smaller than the apparent size of the full moon. To measure it required years of careful observation, exquisitely stable instruments, and a tolerance for cosmic scale precision that bordered on the absurd. The results were announced in 2011. The gyroscopes had drifted by exactly the amount Einstein had predicted. Frame dragging was real. The mass of the Earth, simply by rotating, was twisting the geometry of space around itself. For supermassive black holes, the effect is enormous. Near a rapidly spinning black hole, frame dragging becomes so severe that there is a region outside the event horizon where you cannot stand still. The space itself is being whipped around so fast that no matter how powerful your engines, you cannot resist the swirl. You are forced to orbit along with the spin. This region is called the ergosphere. The ergosphere has one strange property that physicists love to discuss. You can extract energy from a spinning black hole by dropping objects into the ergosphere and having them break apart in just the right way. The pieces that fly outward come back faster than they went in, carrying away some of the black hole's rotational energy. Over time, this would slow the black hole's spin. This process is called the Penrose process, named after the British physicist Roger Penrose, and it is, in principle, a way to mine energy from gravity itself. No civilization has ever attempted it, but the math is sound. Frame dragging is not a quirk of strong gravity. It is a fundamental feature of curved space-time around any rotating mass. Earth does it. Very faintly, the Sun does it. More strongly, every planet and every star in the cosmos is whispering a small twist into the geometry around it. Space-time is not a passive stage. It is a thing that flows, and the flow goes much further than rotation. If gravity bends space, then the universe itself, as a whole, must have a shape. The whole cosmos, all of it, is one enormous geometry. And that geometry is decided by everything inside it. Every star, every galaxy, every cloud of gas, every grain of dust, every drop of radiation, every flicker of energy. Add it all up, and you get the shape of the universe. There are 3 possibilities, and they are wonderfully visual. The universe could be closed. Imagine a balloon with galaxies painted on its surface. If you traveled in a straight line, you would eventually loop back to your starting point. The universe would be finite, like the surface of a sphere. Parallel lines drawn anywhere would eventually meet. There would be no edge. You could journey forever and never reach a wall, because there is no wall. You would simply come around again. The universe could be open. Imagine a Pringles chip, or a saddle shape stretched outward in every direction without end. Parallel lines drawn here would never meet. They would grow farther apart over distance. The universe would be infinite, unbounded, expanding outward into more and more space forever. The universe could be flat. This is the version most consistent with current measurements. Imagine an enormous unwarped sheet stretching in every direction. Parallel lines stay parallel forever. The universe is still infinite, still expanding, but the overall curvature on the largest scales averages out to almost exactly 0. The most detailed measurements of the cosmic microwave background, the faint afterglow of the Big Bang, tell us that the universe is flat to within a small margin of error. This is one of the strangest results in cosmology. There is no good reason for the universe to be flat. It could have been wildly curved one way or the other. The fact that it sits almost exactly on the boundary between open and closed has puzzled physicists for decades, and the leading explanation is a theory called inflation. In the first fraction of a second after the Big Bang, the universe expanded so rapidly that any initial curvature was stretched out to near zero, the same way a wrinkled balloon becomes smooth when you blow it up to the size of a building. So the cosmos is flat on the largest scales, but within that flatness, the geometry is far from uniform. Every massive object creates a local dimple. Every galaxy curves its surroundings. Every black hole gouges a deep pit into the cosmic fabric. Light traveling across the universe weaves through this lumpy landscape, bending around galaxies, slowed by deep gravitational wells, redirected by every concentration of mass it passes. When astronomers look out at distant galaxies, they are not seeing them in a perfectly straight line of sight. They are seeing them at the end of a slightly winding road, shaped by everything between us and them. The deeper the road dips through a massive object, the longer the journey takes, and the more the image is distorted. This is what gravity does at the largest scale. It sculpts the shape of everything. The visible universe is 14 billion light-years across and contains roughly 2 trillion galaxies, and every one of them is sitting in a geometry decided by every other one. But there is a problem. When astronomers add up all the visible mass in the universe, the galaxies, the stars, the gas, the dust, the radiation, the answer is not enough to explain the shapes we see. Galaxies rotate faster than they should. Clusters of galaxies hold together more tightly than they should. Light bends around them more than the visible mass can account for. Something invisible is there, something massive, something we cannot see. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. He measured how fast the individual galaxies in the cluster were moving. The speeds were too high, far too high. If the cluster contained only the visible matter that astronomers could see, the galaxies should have flown apart long ago. The gravity from the stars and gas was not nearly strong enough to hold them together. Zwicky did the calculation and concluded that something else must be present, some kind of invisible mass, hundreds of times more abundant than the visible matter, providing the extra gravity needed to keep the cluster bound. He called it dark matter. The name was a placeholder. It still is. Almost 100 years later, we still do not know what dark matter is. We only know that the universe is full of it. The evidence has grown overwhelming. In the 1970s, the American astronomer Vera Rubin studied the rotation of individual galaxies. She measured how fast stars at the edges of galaxies were orbiting the center. The outer stars should have been moving slower than the inner stars, the same way Neptune orbits the Sun more slowly than Mercury. Instead, the outer stars were moving just as fast as the inner ones. Galaxies were spinning as if they were embedded in giant invisible spheres of mass, extending far beyond the visible disk. Without the dark matter, the galaxies would tear themselves apart. The centrifugal force would fling the outer stars into intergalactic space. Whatever is holding them in place is not glowing. It does not emit light. It does not reflect light. It does not absorb light. It is dark in every sense, except for the gravity it produces. About 5% of the universe is ordinary matter, the kind that makes up stars and planets and people. About 27% is dark matter. The rest is something else entirely. The visible cosmos, the part we can actually see with telescopes, is a small slice of what is out there. Astronomers have mapped dark matter using gravitational lensing. By measuring how much background light is bent by foreground galaxies, they can calculate where the mass really sits. The maps that emerge are extraordinary. Dark matter forms enormous branching structures that thread through the universe like a cosmic web. Galaxies sit at the nodes of this web, like beads on invisible strings. The visible cosmos is the foam riding on top of a much larger ocean we cannot see. What is dark matter actually made of? The leading theories propose unknown particles that interact with ordinary matter only through gravity. Experiments deep underground, shielded from cosmic rays by miles of rock, have been hunting for these particles for decades. So far, nothing. The detectors sit silent. Whatever dark matter is, it does not want to talk to us. Some physicists have proposed that dark matter is not particles at all, but a modification of gravity itself. Maybe Newton and Einstein's laws are slightly wrong at galactic scales, and we are seeing the effects of a deeper theory we have not yet discovered. This idea, called modified Newtonian dynamics, has its supporters, but most of the evidence still points to invisible particles of some kind. Whatever it is, dark matter outweighs everything we can see by a factor of about 5 to 1. The galaxies that fill our telescopes are floating in something else, something that bends space-time massively, but reveals itself only through gravity. And as strange as dark matter is, it is not the strangest thing in the cosmos. There is also something pushing the universe apart. In 1998, 2 independent teams of astronomers were measuring the expansion of the universe. They expected to find that the expansion was slowing down. After all, every galaxy in the cosmos pulls on every other galaxy through gravity. That mutual attraction should act as a brake on the expansion, gradually pulling the cosmos back toward itself. The only question was how fast it was slowing. The teams found the opposite. The expansion of the universe is not slowing down, it is speeding up. This was one of the most shocking discoveries in the history of science. The 2 teams used distant supernovas as cosmic mile markers. A particular kind of exploding star, called a Type 1a supernova, always produces almost exactly the same brightness. By measuring how dim these supernovas appear, astronomers can calculate how far away they are. By measuring their redshift, the stretching of their light as the universe expands, astronomers can calculate how fast they are moving away from us. The data showed that the most distant supernovas were dimmer than expected. They were farther away than the simple expansion of the universe should have placed them. Something was pushing them away faster than gravity should allow. Whatever it was, it had to be enormously powerful, and it had to fill the whole cosmos. The unknown agent was given a name: dark energy. Like dark matter, the name is a label for our ignorance. We do not know what dark energy is, we only know what it does. It accelerates the expansion of the universe, it pushes galaxies apart, it is gravity working in reverse. The leading model says that dark energy is a kind of energy built into the fabric of empty space itself. Every region of vacuum carries a tiny amount of this energy. The more space there is, the more dark energy there is. As the universe expands, more space appears, and more dark energy appears with it. The push grows, the expansion accelerates. The cosmos pulls itself outward, faster and faster. Current measurements show that dark energy makes up about 68% of the universe. Combined with dark matter, that means about 95% of the cosmos is made of stuff we cannot identify. Only 5% is the familiar matter of atoms, stars, and planets. The implications for the future are stark. If dark energy continues to push the universe outward at an accelerating rate, distant galaxies will eventually move away from us faster than the speed of light. They will not break the speed limit in their local space, but the space between us and them will grow so quickly that no signal could ever cross the gap. Those galaxies will fade from view, red shifting into invisibility, until only our local cluster remains visible against an empty black sky. This far future, trillions of years from now, has a name. Cosmologists call it the heat death, or, in more dramatic terms, the Big Freeze. The universe will not collapse. It will not explode. It will simply stretch itself thin until every region of space is so far from every other region that nothing can ever interact again. Some theories suggest a more violent end. If the strength of dark energy increases over time, the acceleration could grow so extreme that even galaxies, stars, planets, and eventually atoms themselves get torn apart by the expansion. This scenario is called the Big Rip. The fabric of space in this case becomes too aggressive for any structure to survive. We do not know which fate awaits the cosmos. We do not even know what dark energy really is. We only know it is winning. The universe is being pushed outward by something invisible, and that something accounts for most of the energy in existence. This is the boundary of what we understand, and the closer we look, the more it cracks. In 1917, Einstein had just finished his theory of general relativity. He turned his equations on the universe as a whole and discovered something he did not like. The math predicted that the cosmos should either be expanding or contracting. It could not stay still. The universe, according to his own theory, was inherently unstable. At the time, every astronomer believed the universe was eternal and unchanging. Galaxies sat where they sat. Stars stayed where they were. The cosmos as a whole was assumed to be the same forever. So Einstein, faced with equations that contradicted what everyone believed, added a fudge factor. He called it the cosmological constant, represented by the Greek letter lambda. It was a term he sprinkled into his equations specifically to keep the universe static. With lambda in place, the math allowed a cosmos that neither grew nor shrank. A few years later, the American astronomer Edwin Hubble proved that the universe was, in fact, expanding. Distant galaxies were moving away from us. The light from them was stretched, shifted toward the red end of the spectrum, exactly as if space itself were stretching. Einstein's original equations, without the fudge factor, had been right all along. He had abandoned his own correct prediction to match the prejudices of his time. When Einstein learned of Hubble's discovery, he reportedly called the cosmological constant the biggest blunder of his life. He had introduced an unnecessary correction to make the math fit a false assumption. If he had trusted his original equations, he could have predicted the expansion of the universe more than a decade before it was observed. He could have been the man who told the world the cosmos was growing. Instead, he played it safe, and Hubble got the credit. Einstein quietly removed the cosmological constant from his equations and moved on. For about 70 years, the constant was treated as a historical embarrassment, a footnote, a lesson about not letting cultural assumptions override the math. Then, in 1998, the discovery of dark energy changed everything. The accelerating expansion of the universe demanded an explanation. Something had to be pushing space outward. When physicists looked for a term in the equations of general relativity that could produce exactly that effect, they found one: the cosmological constant. Einstein's biggest blunder turned out to be the leading candidate for one of the most important features of the cosmos. The constant, if it has a non-zero value, fills empty space with a kind of pressure that pushes outward. It does not behave like ordinary matter. It does not dilute as the universe expands. It is intrinsic to space itself. Add lambda to the equations of general relativity, set its value just right, and you get an expanding cosmos that accelerates over time. Exactly what the supernova observations had revealed. Einstein's correction, abandoned as a mistake, has been resurrected as one of the deepest mysteries in physics. Whether dark energy really is the cosmological constant, or some more exotic phenomenon that merely behaves like one, is still being debated. The value the constant takes is also strange. Quantum field theory predicts that empty space should contain an enormous amount of energy, far more than what we observe. The actual value of the cosmological constant is about 10 to the 120 power times smaller than the naive prediction. This is sometimes called the worst prediction in the history of physics. Theory says one thing, measurement says another. The mismatch is so vast that it cannot be a coincidence. Something fundamental about the relationship between gravity and quantum mechanics is missing from our understanding. And that missing piece is the deepest crack in modern science. Hold a small magnet near a paperclip on the floor. The paperclip jumps up to meet the magnet, lifting off the ground. The entire planet Earth, with its trillions of tons of mass, is pulling that paperclip downward with its full gravity. The little magnet, weighing perhaps a few grams, easily wins. Gravity loses badly. This is one of the strangest facts about gravity. It is, by an enormous margin, the weakest of the four fundamental forces in the universe. Physicists have identified four fundamental forces: the strong nuclear force, which holds the nuclei of atoms together; the electromagnetic force, which governs everything from magnets to chemistry to light; the weak nuclear force, which controls certain kinds of radioactive decay; and gravity, which pulls everything with mass toward everything else with mass. Of these four, gravity is the runt. By an unimaginable margin, the strong force is about 10 to the 38th power times stronger than gravity. That is 1 followed by 38 zeros. The electromagnetic force is about 10 to the 36th power times stronger. Even the weak force, the second weakest, is around 10 to the 25th times stronger than gravity. These numbers are so large that they do not feel like numbers anymore. They feel like a category mistake, as if gravity belongs to a different game entirely. And yet, gravity rules the cosmos. The other three forces, despite their staggering strength, are short-range or self-cancelling. The strong and weak nuclear forces only operate over distances smaller than an atomic nucleus. They are crucial inside particles, but they fade to nothing beyond that scale. The electromagnetic force is long-range, but it comes in two flavors, positive and negative, which cancel each other out almost perfectly on large scales. Most of the universe, viewed from far away, is electrically neutral. Gravity has none of these handicaps. It is always attractive. It never cancels itself out. It has no opposite charge. Every bit of mass and energy adds to the gravitational total. Over cosmic distances, the tiny weakness of gravity per atom becomes enormous when summed over trillions of atoms. The Sun is mostly held together by its own gravity. The Moon orbits Earth because of gravity. Entire galaxies form because of gravity. Why is gravity so weak? Nobody knows. This is called the hierarchy problem, and it is one of the deepest unsolved puzzles in physics. There is no known reason why gravity should be so absurdly feeble compared to the other forces. Some theorists have proposed exotic explanations. Maybe gravity is actually as strong as the other forces, but most of it is leaking into extra dimensions of space that we cannot see. Maybe what we feel here is only the small fraction of gravity that lives in our familiar 3 dimensions. This idea sounds wild, but it has been taken seriously enough that physicists at the Large Hadron Collider in Switzerland have looked for evidence of extra dimensions in their particle collisions. So far, no extra dimensions have been found. Gravity remains, as best we can tell, intrinsically and stubbornly weak. There is a strange consequence to gravity's weakness. It is the only one of the 4 forces that has not yet been described by quantum mechanics. The other 3 have all been incorporated into the framework of quantum field theory. Each of them has been broken down into particles that carry the force. Photons carry electromagnetism. Gluons carry the strong force. W and Z bosons carry the weak force. Gravity should have a particle too, called the graviton. We have never seen one. We may never see one. Because the moment you try to combine gravity with quantum mechanics, everything breaks. There are 2 pillars of modern physics. General relativity describes the very large: stars, galaxies, black holes, the cosmos itself. Quantum mechanics describes the very small: atoms, electrons, photons, the strange behavior of subatomic particles. Both theories work with breathtaking precision in their own domains. Both have been tested thousands of times. Both have never been wrong, and they cannot be combined. This is the central problem of theoretical physics. Quantum mechanics and general relativity are mutually incompatible. try to make them speak the same language, and the math collapses into nonsense. Predictions diverge to infinity. Calculations produce probabilities greater than 1. The two best theories humanity has ever produced refuse to agree on how the universe works. The reasons run deep. Quantum mechanics treats space and time as a fixed background, a stage on which particles dance. General relativity treats space and time as the dance itself, warping and bending in response to mass and energy. In quantum mechanics, the equations need a clear sense of time to evolve probabilities. In general relativity, time is local, varying from place to place, with no universal clock. The two theories are built on incompatible foundations. For most everyday physics, this incompatibility does not matter. Quantum mechanics rules at small scales, where gravity is negligible. General relativity rules at large scales where quantum effects average out. The two theories work in different domains and never have to talk to each other. But there are situations where they do have to talk. The center of a black hole, where matter is crushed into a region small enough that quantum mechanics should dominate. But gravity is so strong that general relativity is also essential. The first moments after the Big Bang, when the entire universe was smaller than an atom, and unimaginably hot. In these extreme conditions, both theories apply, and both theories break. The dream is a theory of quantum gravity, a single framework that combines the geometry of general relativity with the probabilistic nature of quantum mechanics. Physicists have been chasing this dream for nearly a century, and they have not caught it yet. Einstein himself spent the last decades of his life searching for a unified theory, and failed. Some of the brightest minds since have devoted entire careers to the problem, with no clear breakthrough. Several approaches have emerged. String theory proposes that every particle in the universe is actually a tiny vibrating loop of energy, and that gravity arises naturally from the way these loops behave. The theory has elegant mathematical features. It also requires extra dimensions of space, possibly as many as 11, most of which are curled up too small to observe. String theory has produced beautiful ideas, but no experimental confirmation. The energies needed to test it directly are far beyond anything humans can currently produce. Another approach is loop quantum gravity. This theory proposes that space itself is not continuous, but is made up of tiny discrete chunks, like the pixels of a screen. At very small scales, space stops being smooth and becomes grainy. The geometry that Einstein described would emerge as an average over many tiny quantum bits of space. A third path imagines space-time itself as an emergent phenomenon, the way temperature emerges from the motion of atoms. In this view, what we call space and time are not fundamental. They are a kind of statistical description of something deeper, something we have not yet discovered. None of these theories is confirmed. None makes predictions that current experiments can test. The problem of quantum gravity remains open, and it remains the deepest open problem in theoretical physics. What we do know is that somewhere underneath our current theories, there is a single description of nature. Gravity and quantum mechanics must in some way be the same thing. We just do not yet speak the language. Every force in the universe, as far as we know, is carried by a particle. The electromagnetic force is carried by photons. The strong nuclear force is carried by W and Z bosons. Each of these particles has been detected in real experiments. They are part of the standard model of particle physics, the framework that describes everything we have ever observed in particle colliders. Gravity should have a particle too. Physicists call it the graviton. If quantum field theory applies to gravity the way it applies to the other three forces, then every gravitational interaction should involve the exchange of these tiny carriers. The graviton would be massless, like the photon, and travel at the speed of light. It would have a spin of 2, distinguishing it from the spin 1 particles of the other forces. The math of a graviton is, in some ways, well understood. Physicists can write down the equations describing how gravitons should behave at low energies, Those equations agree with general relativity in the appropriate limits. The graviton is, in this sense, the natural quantum description of gravity. But there is a problem, a serious one. When physicists try to use the graviton to calculate what happens at very high energies, close to the strength of gravity at extremely small distances, the math explodes. The calculations produce infinite answers for quantities that should be finite. The graviton is not renormalizable, which is a technical way of saying that the theory cannot be tamed at the highest energies. Something is missing. There is also a more practical problem. The graviton has never been detected. It probably never will be. The interaction strength of an individual graviton with ordinary matter is so weak that no instrument humans can imagine building would be sensitive enough to spot one. The famous calculation by the physicist Freeman Dyson estimated that to detect a single graviton, you would need a detector the size of Jupiter, made of materials denser than neutron stars. And even then, you would need to wait many times the age of the universe to catch one. The graviton may be permanently beyond direct experimental reach. We may have to settle for indirect evidence, hints from cosmology, patterns in the cosmic microwave background, signatures in the merger waveforms detected by LIGO. None of those will ever amount to seeing a graviton the way physicists have seen a photon. This makes gravity unique. It is the only force whose carrier particle may be undetectable in principle, not just in practice. The other three forces have been broken down into their building blocks. Gravity may forever resist that kind of decomposition. Some physicists wonder if this is a clue. Maybe gravity is not really a force at all, in the same sense as the others. Maybe it is something deeper. Maybe what we call gravity is really a side effect of some more fundamental phenomenon, and the search for a graviton is the wrong search entirely. The same way we no longer look for a particle that carries the force of friction, because friction turned out to be a statistical effect of many smaller interactions. Gravity might turn out to be something other than a fundamental force. The Indian physicist Ted Jacobson in 1995 showed that Einstein's equations of general relativity can be derived from thermodynamic principles, the same kind of principles that govern heat and entropy. This suggests that gravity might be an emergent phenomenon, a kind of cosmic statistics, rather than a fundamental ingredient of the universe. If gravity is emergent, then there is no graviton. There is only something deeper beneath both space and time from which gravity arises. And one candidate for that something deeper is a theory that has shaped physics for 40 years. In the late 1960s and early 1970s, a group of physicists began studying a strange new idea. What if the fundamental ingredients of the universe were not point-like particles, but tiny vibrating strings of energy? Each kind of particle, electron, photon, quark, would simply be a different mode of vibration of these strings, like different notes played on the same instrument. The whole zoo of particles in nature would emerge from one underlying entity. This was the beginning of string theory. And one of its earliest surprises was that when physicists worked out the mathematical consequences, the theory automatically predicted gravity. There was a particular vibration mode of the strings that had exactly the properties of a graviton. The math demanded it. You could not write down a consistent string theory without including gravity. After decades of trying to combine gravity with quantum mechanics by hand, here was a theory in which the union was built in from the start. This was exhilarating. It was also strange, because string theory required more than the usual 4 dimensions of space-time. In its earliest version, it needed 26. Later refinements, called superstring theory, reduced this to 10. Still later refinements, called M-theory, settled on 11 dimensions as the natural setting. 11. 1 dimension of time and 10 of space. 7 of those spatial dimensions are not visible to us. They are thought to be curled up into incredibly tiny shapes, far smaller than an atom, hidden from direct observation. Imagine a garden hose seen from very far away. From a distance, the hose looks like a one-dimensional line. Up close, you can see that the line is actually a tube, with an additional curled-up dimension wrapping around it. String theorists propose that the universe is like this. We see 4 large dimensions, but the rest are too small to detect. The geometry of those hidden dimensions matters enormously. The specific shape of the curled-up dimensions determines what particles exist in our universe, what masses they have, and how they interact. Change the geometry, and you change the laws of physics. String theory, in principle, allows for an enormous number of possible configurations, called the string landscape. Some estimates put the number of possible universes string theory permits at 10 to the 500th power. That is a 1 followed by 500 zeros. This vast landscape is both a strength and a weakness. A strength because it might explain why our universe has the particular properties it does. Out of that staggering number of possibilities, ours is one of the rare configurations that allows complex chemistry, stable stars, and life. A weakness because with so many possibilities, it becomes very hard to make specific testable predictions. Critics argue that any theory that can predict anything predicts nothing. After 50 years of work, string theory has not produced a confirmed experimental prediction. The energies needed to test the theory directly are far beyond anything humans can produce. The Large Hadron Collider operates at energies trillions of times too low to probe the string scale. To test string theory directly, you would need a particle accelerator the size of the solar system, possibly the size of the galaxy. This has led some physicists to abandon string theory. Others remain convinced that it is the most promising approach to quantum gravity, despite the lack of experimental confirmation. String theory has, at the very least, produced extraordinary mathematical insights, deepened the understanding of black holes, and forged unexpected connections between distant areas of physics. Whether or not it is the final answer, string theory has changed how physicists think about gravity. It has made the union of gravity and quantum mechanics seem possible, if only on paper. There is one alternative that takes a very different approach. What if space itself is not smooth? What if, at the smallest scales, the universe is made of tiny chunks, like the pixels of a digital image? This is the central idea of loop quantum gravity. Unlike string theory, which keeps the geometry of space-time continuous and adds extra dimensions, loop quantum gravity treats space itself as fundamentally grainy. At very small distances, the smooth geometry of general relativity dissolves into discrete units. There is a smallest possible volume of space, called a quantum of geometry, and you cannot get smaller than that. The scale at which this graininess would appear is the Planck length, about 10 to the negative 35th meters. That number is so absurdly tiny that calling it small does not do it justice. If you took a single hydrogen atom and shrank it down to the size the entire observable universe is shrunk relative to itself, you would still be much larger than a Planck length. It is the smallest unit of distance that has any physical meaning, according to our current theories. At this scale, loop quantum gravity says, space stops being continuous. It breaks up into a network of tiny loops and nodes, a kind of spinfoam. Time, too, would be discrete in this picture, advancing in tiny jumps rather than flowing smoothly. The continuous geometry of Einstein's theory would be an emergent average over many of these microscopic quantum bits. The appeal of loop quantum gravity is that it does not require extra dimensions or new particles. It works within the 4 dimensions of space-time that we already know. It also makes some interesting predictions. One is that the singularity at the center of a black hole, where general relativity says density becomes infinite, would not actually exist. The discrete structure of space would prevent matter from being crushed to a single point. Instead, the collapse would halt at some small but finite size, and the resulting object would be a kind of quantum remnant. Loop quantum gravity also offers a possible resolution to the Big Bang singularity. Instead of the universe beginning from a point of infinite density, the theory suggests it may have bounced from a previous contracting phase. A bouncing cosmology, in which the universe undergoes endless cycles of expansion and contraction, becomes possible if space has a smallest unit of volume. Like string theory, loop quantum gravity remains untested. The graininess of space at the Planck scale is far too small to observe directly. Some indirect tests have been proposed. Maybe the discrete structure of space causes light of different energies to travel at slightly different speeds over very long distances. By comparing the arrival times of high-energy and low-energy photons from distant gamma-ray bursts, astronomers can look for tiny delays that might indicate quantum gravity effects. So far, no clear signal has emerged. The two approaches, string theory and loop quantum gravity, represent very different visions of the deep structure of nature. String theory keeps geometry continuous and adds new ingredients to make quantum mechanics fit. Loop quantum gravity keeps the ingredients minimal and changes the geometry. Both might be wrong. Both might be partial glimpses of something larger. There is no consensus. There is no winning theory. There is only the conviction shared by most physicists that somewhere underneath our current understanding lies a deeper description in which gravity and quantum mechanics become one thing. And the most radical idea of all is that gravity might not be a fundamental force in any of the ways we have imagined. In 2010, a Dutch physicist named Erik Verlinde proposed something startling. Gravity, he said, is not a fundamental force at all. It is not a feature of space-time curvature. It is not carried by gravitons. It is an emergent phenomenon, a side effect of something deeper, like the way temperature emerges from the motion of countless atoms. In Verlinde's picture, what we call gravity is really a manifestation of how information is organized at the most fundamental level of reality. When information is rearranged, when bits of cosmic data shift their positions, the result is a force that looks exactly like gravity. The pull you feel toward Earth is not really a pull. It is the universe rearranging its own information in a way that happens to produce the appearance of attraction. This idea sounds wild. It might be wrong, but it is built on serious mathematics, and it connects to ideas that have been brewing in physics for decades. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered that black holes have a temperature and an entropy. The entropy of a black hole is proportional to the area of its event horizon, not to the volume inside. This was deeply strange. In most physics, entropy is a property of a three-dimensional region. For black holes, it lives on a two-dimensional surface. The information content of the black hole somehow scales with the boundary, not the interior. This led to what is now called the holographic principle. The idea, developed further by Gerard Hooft and Leonard Susskind in the 1990s, is that the information content of any region of space is fully described by information living on its boundary. A three-dimensional volume of space is in some sense a kind of projection of a two-dimensional surface. Reality might be a hologram. The depth we experience might be encoded on a distant surface, far away in conceptual space. If the holographic principle is true, then gravity, which we perceive as something happening in the three-dimensional bulk of space, must be a kind of emergent effect of information flowing on a two-dimensional boundary. Verlinde's theory of entropic gravity is one specific attempt to flesh out this idea. The mathematics has been refined over the past 15 years. Some calculations show that entropic gravity reproduces Newton's law of universal gravitation in the appropriate limits. Some attempts to extend it have run into problems with explaining how it should connect to general relativity in its full form. The theory remains controversial. Some physicists find it deeply promising. Others find it speculative and unfinished. What is striking is that even if Verlinde's specific proposal is wrong, the underlying intuition keeps appearing in different forms across modern theoretical physics. The idea that space-time and gravity along with it is not fundamental, but emergent, has become a serious area of research. Conferences are held on it, papers are written, careers are built on the assumption that reality at its deepest level is not geometric. If this is right, then gravity is not even a feature of the universe. It is a feature of how we perceive a deeper reality. The fabric of space-time, the curving geometry that Einstein described so beautifully, would be a kind of illusion, a smooth picture painted by something else underneath. We do not know if this is true. The experiments are not yet able to settle the question. But the possibility that gravity, the most familiar phenomenon in our daily lives, might not exist in the way we imagine, is one of the most thrilling possibilities in modern science. And the deeper questions only multiply. Step back and look at what we have learned. Gravity, according to our best current theory, is not a force. It is the curvature of space-time caused by mass and energy. Objects in gravitational fields are not being pulled. They are gliding along the natural geometry around them. Time itself runs at different rates depending on where you are in that geometry. Light bends, space stretches, black holes warp the fabric of reality so severely that time and space change roles inside them. This picture has been confirmed by every experiment we have ever performed. The orbit of Mercury, the bending of starlight by the sun, the slowing of clocks at lower altitudes, the 38 microseconds per day correction needed for GPS satellites, the detection of gravitational waves from black hole mergers a billion light years away, the image of Sagittarius A star at the center of our galaxy, the slow twisting of space-time by the rotating Earth, confirmed by gyroscopes in orbit. Every test of general relativity, in every regime in which it has been tested, has come back successful. And yet, the theory is incomplete. At the singularity inside a black hole, general relativity breaks down. The equations produce infinities, which physics interprets as a sign that we are missing something deeper. At the Big Bang, the same problem appears. The earliest moment of the universe involves a state of infinite density that the theory cannot describe. At the smallest scales, quantum mechanics takes over, and our two best theories refuse to merge. We do not know what dark matter is. We do not know what dark energy is. Combined, they make up about 95% of the contents of the universe. The familiar matter we see, the atoms that make up stars and planets and people, is a tiny minority of the cosmos. The rest is mystery. We do not know why gravity is so weak compared to the other forces. We do not know if the graviton exists as a fundamental particle, or if gravity is an emergent phenomenon. We do not know if space has extra hidden dimensions. We do not know if space-time is continuous or grainy at the smallest scales. We do not know if the universe is finite or infinite. We do not know if there are other universes, or if our cosmos is one of many. What we do know is that gravity is the most pervasive feature of the universe. It shaped the formation of stars from clouds of hydrogen. It pulled rocks together to make planets. It built galaxies. It seeded the structures we see in the cosmic microwave background. It allows tides. It allows orbits. It allows the very existence of complex structures like life. Without gravity, the universe would be a thin, uniform soup of particles with no organization, no stars, no planets, no chemistry, no biology. Gravity is also intimate. It shapes your bones. Astronauts who spend months on the International Space Station lose bone density because their bodies adapted to a planet's pull over hundreds of millions of years of evolution. Take that pull away and the body begins to dissolve. Our biology is, in a literal sense, sculpted by space-time curvature, and every step you take, every breath, every heartbeat, happens inside a region of warped geometry. Earth is bending space and time around itself constantly. Your phone's location services account for this curvature. Your car's navigation depends on it. The technology of modern civilization rests on equations that were once written by hand on chalkboards in 1915. There is a humility in all this. Einstein gave us a description of gravity that has stood for over a century. The theory has been pushed to its limits, tested in extreme environments, applied to objects from atoms to galaxies. It has not failed, but it has also not finished. Something deeper waits. And the search for that something deeper is the great adventure of physics now. Pause here at the end of this journey and look at what we have actually been chasing. Not just gravity, not just space-time, not just black holes and dark energy and the strange geometry of the cosmos. Underneath every chapter of this story is a single question: what is real? For 2,000 years, humans assumed space and time were the unchanging stage on which everything happened. The cosmos was a vast, empty container, and matter moved within it. Galileo, Newton, even most of the early modern physicists accepted this picture. Space was a backdrop. Time was a river. Both flowed independently of what they contained. Einstein changed that. He showed that space and time are not background. They are participants. They bend. They stretch. They flow differently in different places. The stage is part of the play. The container is part of the contents. That alone was a revolution. But the revolution has not stopped. The deeper we look, the more space and time themselves begin to dissolve. Quantum mechanics suggests that at the smaller scales, reality is probabilistic, granular, strange. Loop quantum gravity suggests that space is made of tiny discrete pieces. String theory suggests that there are more dimensions than we can perceive. Holographic theories suggests that what we see as three-dimensional space is really a projection of something simpler. Entropic gravity suggests that the pull we feel is not even a fundamental thing. If any of these ideas turn out to be true, the implications go beyond physics. They reach into questions about the nature of reality, the meaning of experience, the structure of perception itself. The geometry we live in might be a kind of user interface, a simplified picture our minds construct from something far more abstract underneath. This is not mysticism. This is where the math is taking us. Physicists who have spent their careers working on quantum gravity say openly that space-time is probably emergent. Some of the deepest researchers in the field, people like Edward Witten and Juan Maldacena, have spent decades following the trail of evidence that suggests the universe we see is a translation of something beneath it that we have not yet understood. If they are right, then gravity is the doorway. It is the phenomenon where the cracks in our understanding open widest. To understand gravity is to begin understanding what reality really is. And we are nowhere near done. The instruments are getting better. LIGO is being upgraded. New gravitational wave detectors are being designed. The European Space Agency is planning LISA, a space-based observatory that will use 3 satellites orbiting the Sun, separated by millions of miles, to detect gravitational waves at frequencies that ground-based instruments cannot reach. The next generation of cosmological surveys will map dark matter and dark energy across cosmic time. The James Webb Space Telescope is peering deeper into the universe than any instrument before it. New ideas are being tested, old assumptions are being questioned. We are living in one of the great eras of physics, possibly the greatest since the years that gave us general relativity and quantum mechanics. We are surrounded by mystery, and we have the tools to start cracking it open. The next time you stand up from a chair, the next time you watch something fall, the next time you walk down a flight of stairs, remember what is actually happening. You are inside a warp. The geometry around you is curving. Time is running slightly slower at your feet than at your head. Space is being twisted by every massive object in the room. The building, the planet, the galaxy. You are not in space. You are in a shape, drawn by every particle in the cosmos. Gravity is not what you were taught. It never was. And the deepest part of the story is still being written.